Yeah. Okay, so just somebody confirm my slides are visible and I'm audible.
Yes, sir.
Yes, sir.
Thank you, thank you. Okay, so let me quickly review what we did in the last class on the Carnot map. So the purpose is to minimize so that we have an optimal uh, two level, in the sense that you have a sum of product, or we'll see today that also possibly also a product of some form. And it uses the uh, it tries to identify patterns where you have two terms in the form in the following form, where p is let p be a sub expression. You have pz as well as pz bar. Pz, the z is in uncomplemented as well as complemented from both literals are there. Then you can replace pj or pj bar as just p. So basically, you eliminate the variable z. Okay, so this is actually represented, as you all know, as an Carnot map, where what you basically do is that you form a table kind of structure where every cell corresponds to a min term. Every cell corresponds to a min term. Min term means, as you all know, it's a product of literal, either complemented or uncomplemented. And if you denote the min terms in the following way, that means 0, 0 means C bar and D bar, whereas 0, 0 here means A bar and B bar. Similarly, 0, 1 in the CD columns means C bar and D. So if you map all the min terms, note that we mentioned that it will not be in the binary order, but rather in the gray order, because what we actually want is that two adjacent min terms. Adjacent meaning they share an edge. Two adjacent min terms will differ in exactly one variable. They will differ in the value of exactly one variable. So that's what we call the min term. So if you look at any two adjacent cell, they differ in exactly one variable. And then from the truth table of the function, say we are trying to minimize a function f, from the truth table of the function, you pick up the true min terms, the min terms where the truth table gives 1, and mark them. So there is we already seen that you can actually write it down by and see, these numbers are like, if you write it as binary, say for example, this is 0, 0, 0, 0, convert it into decimal, corresponding numbers you mark, the true min terms. So this is the notation called the sigma notation, where f is represented as sigma over all the min terms, small m. The min terms are, the true min terms are 0, 7, 9, 12, and 15. These are the true min terms. Now, in this, so basically you can represent f as the first min term, 0th min term plus the 7th min term is the sum of product from min terms are products, plus the 9th min term plus the 12th min term. And what is the 7th min term? For example, the 7th min term is this one. So it is 0, 0, 1, 1, which means A bar, B, C, D. This is the 7th min term. So this way you express a function. Now, since they are this kind of geometrically laid out in 2 dimension, and the rows and columns are in this adjacent order, so that adjacent cell differs by one variable, you can easily identify these patterns. You can easily identify presence of PZ and PZ bar from the location of the true min terms. And moment you identify them, you absorb them and you eliminate the Z variable. Okay, so that's the idea. So that's how you do a minimization. So this is a Carnot map for 4 variables A, B, C, and D. Okay, so let us quickly, this is an example what we have told. So this is an function These are all the min. So this is a sum of product from. So I can express the function as sum of these min terms. And I have written down some of the true min terms as that. So I have marked the true min terms as blue here. And you can see this is a pair of min term. So now let us quickly specify the rules. What we do was we tried to cover the true min terms, the cells marked blue here, using cubes with the property that every cube has to be consisting of adjacent cells and has to have a size in the form 2 to the power k. So it has to be, it can be either be a 2-cell cube or a 4-cell cube or an 8-cell cube. So this is a 2-cell cube, and once you identify such cube, you can easily identify the variables which can be eliminated if we consider the whole cube. For example, there's an easy way to eliminate the variable. You look at all, you write down all the min terms, the true min terms that lie inside the cube, and you see which variable is present or which set of variables are present both in complemented and uncomplemented. For example, here you see the variables C and D both are 1. They do not change. They are constant over the cube. Similarly, the variable B is also constant over the cube. Only the variable A varies over the cube. It's both 0 as well as 1 in the cube. So A can be eliminated. And now if we write the reduced min term, what you get is that you just look at the form. So it is 1, 1. So it will be CD. B is also 1. So BCD is the min term corresponds to D. This you can actually algebraically verify also. I mean, it's trivial actually. So if you look at BCD here and BCD here, you see A and A bar are both there. So they get eliminated. A plus A bar is 1. This is a separate min term which is not eliminated, not reduced. This is another min term which is not reduced. So your total reduced expression will be BCD plus this min term plus this min term plus this min term. Okay, so this is what it will be. Right, so here is another example. In the sigma notation, you have the true min terms are 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. These are the true min terms. So now what we will, again, let me repeat the goal. The goal is to cover all the true min terms using cube, form cubes consisting of adjacent cells of size 2 or 4 or 8. Try to form as large cube as possible. One thing I think you still remember is that the definition of adjacent cell is that they differ in just one variable. They differ in just one variable. So it also means that not only these are the adjacent cubes, but this and this, you can sort of wrap around this both vertically and horizontally. So 0, 0 and 1, 0, these are also adjacent cubes. These are also adjacent cubes. Similarly, 0 and 2 is also adjacent cube. 0 and 8 is also adjacent cube. Adjacent cells, not adjacent cube, adjacent cells. Okay, so these are also similarly 0, 1 and 8, 9 are also adjacent cells. So I think it's obvious that I said that you have to cover up all the true min terms using cubes, and what you want is the cubes to be as large as possible. The meaning is that the larger the cube, so if a cube is of size 2 to the power k, from the set of min terms lying inside the cube, you can remove k number of variables. So larger the cube, the larger number of variables you can eliminate. So your goal is always to form as large cube as possible. Right. In fact, this is a little bit vaguely defined because so there are many possibilities. So what is the minimal set of cube? And I say as large as possible, but I'm not talking of a single cube. I'm talking of multiple cube. So how do you define that this is the minimal set of cubes? Of course, one definition is there. You the final expression should have the minimum number of literals. But this is vaguely defined. We'll later see an algorithm which clearly defines this and clearly defines what is the minimal number of cubes that you can form. Okay, so can anybody tell what are the cubes that we have in this covering cubes that we have in this diagram? Anybody, please quickly tell. Somebody, any of you, just tell the main terms which form a covering cube, large covering cube rather. Okay, let me tell it. So this is one example. This is a cube. I have not yet fully covered, so I need. This is another possible cube. This is another possible cube. So these are the possible cubes I can make to cover this. So let's look this. First, look at this cube. So you see the only thing that is invariant across this cube is C. D varies. C is invariant. C is the only thing that is invariant. A, B both varies. D varies. C is the only, and C is 0. So you should have C. So the first term corresponding to blue will be C bar. Now look at this second, 0, 4, 2, and 6. What are the things that are varying? C is varying, A is varying, no, A is not varying, B is varying, and C is varying. So A and D are invariant. D is in 0 form, A is in 0 form. So it will be A bar, D bar. Now look at this green cube. It will be B, D bar. Right. So in this way you can do it. So here is another example. You can form this cube, whereas you see these are not covered by this cube. So you can form this, you can form this. This is a possible reduction. So this blue one, you see the thing that is not varying is D and B. So you have BD. In the green one, ABC. In that red one, it's AC. No, this orange one, 15 and 11 is ACD, whereas this, sorry, I made a mistake. This green one will be B bar, C bar, D bar. Okay. Now let us see. So this is this. So you can have other such examples also. I hope all of you will practice some examples involving where you can have minimal type. Note that you have to just remember the rules. You have to form cubes. You have to cover all the true main terms. You have to form as large cubes as possible. And the cubes should be consisting of adjacent cells and should be of the size to the power k. That's all. That's all you need. Okay. So you can see other examples also. There are many other examples are possible for this. Okay, so can you give an example of an Carnot map which cannot be minimized at all? You remember we discussed in the last class. Can you tell what type of
one?
XOR diagonal one.
XOR. Or yeah, the diagonal one also cannot be minimized. Okay, so these are some functions, and you can easily look at the corresponding functional form which cannot be minimized. All right, so now let's move on to Carnot maps of involving 5 variables A, B, C, D, and E. So let us see how to do that. So the way you do this is that you look at the pattern. So forget about the right half of this 16 cells, right half cell. Just look at this part. You see, and you forget the E variable. You see, it is the there is a kind of symmetry. So you kind of see that if you look at any two adjacent cell, they just differ by one variable. So this is fine. This is, I think you know that. If you look at the rows, AB rows, I think this pattern is same as the previous. Can you tell something? What is the order in which I have written the CD rows, and that it's easy to verify that all two adjacent cell differs by just one variable. That's easy to verify. I have written it that way. So can you tell anything about the order of the variables 0, 0, 0, 0, 0, 1, 0, 1, 1 that has been written along the columns? That is the CDE variables. What is the
in
pattern?
gray code notation.
Exactly, in gray code. And can you say anything about the that follows from the property of the gray code itself, that what is the relation between the column values for the first 4 columns and the next 4 columns? It follows
So they are
from the
mirror
gray code.
images along the vertical line.
They are mirror images along the vertical line. That's good. Exactly. So that's an important property. We'll see that. Okay. So now let us write out this function. This function consists of the following min terms 1, 2, 3, 4. So these min terms marked blue are the min terms, right? So the same rule follows. You can form cubes using adjacent cells. You can the larger the cube, if you have a 2 to the power k sized cube, you can eliminate k variables. The same things hold, and the earlier rules of forming cube, that for example 0, 1, 8, 9 is a cube, 0, 1, 8, 9, 24, 25, 16, 17 is a cube. By the way, note one thing, look at the order of the decimal numbers corresponding to the min terms. Okay, look at the order. So this is the gray code order. You just look at 0, 1, 3, 2, 6, 7, 5, 4. This order is important. You have written out this. This is an order which will preserve these gray code properties. Right. So 0, 1, 8, 9, 24, 25, 16, 17. This is a cube. This is a 8-sided cube. Okay. This is a and this also holds. For example, 24 and 28, they are neighbors. 24 and 28 are neighbors. Similarly, 0 and 16 are neighbors. That's fine. But there are additional neighbors that you can form. The additional neighbors is anything which is a reflection of each other along this middle vertical axis, So that means the 4th and the 5th column, that separator between the 4th and the 5th column. Any two cells which are left-right mirror images of each other are also adjacent. Let's see. So 10 and 14. You see, they differ by just one variable. So actually the rule is, I mean, of course, the rule should be that because pz plus pz bar is p. That's the rule. So z and z bar means they should be adjacent cells. So you should be able to identify a variable which is the only difference between two min terms, which is then we call them as adjacent. So naturally, the previous rules for a 4x4 variable thing that holds, plus some additional thing holds. For example, 0, 1, 0 is adjacent to 1, 1, 0. It's only changing in the C variable. 0, 1, 0 and 1, 1, 0 is only changed. So 10 and 14 should be a mirror image. 26 and 30 should be a mirror image. 26 and 30 should be a mirror image. 11 and 15 should be a mirror image. 11 and 15 should be a mirror image, right? Similarly, 9 and 13 should be a mirror image. So this can also help you form large cubes. This can also help you form large cubes. So for example, you can see that those are not the true min terms here, but 2, 6, 10, 14, 26, 30, 18, 22, they can as well form a cell. Right? So this is a if you try to visualize it geometrically, this is or for example 3, 11, 27, 19 and 7, 15, 31, 23, they can also form a cube. 3, 7, 11, 15, 27, 31, 19, 23, they can also form a cube. Okay, so this is a bit difficult to visualize geometrically, because the earlier thing that you can fold along the corners or you can fold so that's like a toroid. It's like a torus. That's easy to visualize. This is a 5-dimensional geometry, so it's more difficult to visualize, but it is also actually torus in 5-dimensional geometry. Okay, so can you tell me quickly what are the cubes that I can form in this diagram? Just name the cubes that you can form in this diagram.
The initial block 0, 45, 16, 17.
Okay, so 0, 1, 8, 9, 24, 25, 16, 17. That's one definitely. Anything else?
2, 10, 26, 18.
2, 10, 26, 18. Fine. 7, 15.
28, 24.
28, 24. Anything
26,
else?
30.
26.
24, 26, 30, 28.
26, 30.
24,
28.
28.
Right. 26, 30. 24, 28. Right. 26, 30, 24, 28. Right. So let me draw. So this is one, as you have said. This is one. Because see, the earlier rules also hold. So I can as well fold this 4x4 to form a toroid. So I can horizontally, yes, I can horizontally fold this 4x4 also. So this is also valid. Right. So similarly, this is also valid because these two are adjacent and these two are adjacent, and so these two are adjacent by the reflection rule. These two are adjacent by the toroid rule, and 24 and 26 are again adjacent by the toroid rule. Similarly, 30 and 28 are also adjacent by the toroid rule. Okay, so 24, 26, 30, 28, they are all adjacent. 7, 15, of course. So let us write down. So this 8, 0, 1, 8, 9, 24, 25, 16, 17, they will be C bar, D bar. I'm not explaining, you can easily find out. So the rule is you write down all the binary representation for each of the cubes, and you see which variables are constant and which variables are changing. Changing in the sense they are both complemented and uncomplemented. Remove the changing variables, keep only the constant variables, invariant variables. And look at the invariant variables, they are 0 or 1. Depending on their 0 or 1, you put a bar or don't put a bar. Okay, so C bar D bar is this blue thing. E bar C bar is this 0, 8, 24, 16 followed by 2, 10, 26, 18. This 8, E bar C bar. So 8 means 2 to the power 3. I have removed 3 from 5. I have got 2 variables. This 24, 26, 30, 28, you can easily check that the constant variables are A, B, and E bar. Similarly, 7, 15, you can just remove one variable. So it is A bar, C, D, and E. Okay, so this is the rule. So here, can you tell what are the okay, just one more thing. Let me quickly tell you this formulation. This formulation means, see, this is a sigma expression. This is a sigma type expression. You have two sigmas. One has a subscript of m, and these are the m subscripts. What it means, the true min terms are this, denoted by blues here. There is another set of min terms, which I denote as small d. These min terms are kind of don't cares. These min terms are kind of don't care. What do you mean by don't care? Don't care means that their values are the output corresponding to this combination of input. Either they will not, this combination of input will not ever happen, or whatever is their output, 0 or 1, it's not a problem. You can have any output. Let's take an example. You know that in the BCD representation, you represent decimal digits 0 to 9 using 4 bits. Okay, so you really care about the decimal representation of 0 to 9, but there are uh, six more values that are possible, 6 more input combinations that are possible, corresponding to 10, 11, 12, 13, up to 15. Those combinations are possible. But those combination of inputs, I am not really cared. For example, you are building an 7-segment LED display. You know that input will not only be 0 to 9. You don't bother about the other inputs. You don't bother about the inputs. So what does the 7-segment LED display when you get an input corresponding to, let's say, 11 or 12 or something? You don't really matter, because you have only 1 digit to display in 7-segment display. You cannot display 2 digits. Okay, so those input combinations, either they will not happen, or you are not really bothered about the correctness of the output. You don't know what is the correct output. You are not really bothered about the correctness of the output for those combinations. So those combinations of input would be called a don't care combination. You are not bothered about what that combination is. Okay, so this combination, I am not exactly representing them as true min, because you are not fixed upon that their output value should be 1. So that's why they are not true min terms. But they can be, I am okay with both. I'm okay with if their output is 0. I'm also okay with if their output is 1. So what I do is that I also list them. I also sigma the don't cares. Why I sigma them? There is a reason for this. So in this table, I have, in this diagram, I have marked them as this violet: 31, 19, 18, 1, 0. These are the don't cares. The reason I am including I'm sorry. The reason I'm including this don't care here is the follows. Because since they can take a value 1 or 0, if setting them to 1 helps me create larger cubes, I'll set them to 1. If setting them to 1 helps me draw larger cubes, which means I can minimize the expression further,
Sir, you are muted.
am I audible now?
Yes, sir.
Okay, so I don't know since how long I'm muted, but anyway, so I've also written down the don't cares. These are some min terms for which I do not bother the output is 1 or 0. So what I will conveniently do is that sometimes I'll set their output to 1. I'll treat them as true min terms if they help me to form larger cubes. If they help me to form larger cubes, I'll set them to 1. But on the other hand, I do not have the responsibility to cover all the don't cares. I need not form cubes to cover all the don't cares. I can leave them out because they can be false min terms also. They can as well be false min terms also. So I need not cover all. I need to cover only the true min terms. Okay. So conveniently, so they add to my convenience. If they help me in forming larger cubes, I'll consider them as true min terms. And if they don't help me, I'll consider them as min terms. Okay. So this gives me some flexibility. So here is an example. So you see, if I include this don't care 19, it helps me form this cube 25, 27, 17, 19. Similarly, if anything else, okay. What about this 0, 1 and 21, 20? 0, 1 and 21, 20. Does it help? 0, 1, 21, 20. No, it doesn't help. I think these are the only. Let's see. Let's write down. Okay. So this is a simple by following the reflection rule as well as the wrapping around rule. This is following the wrapping around rule. Note that here this 1 as well as 19, these don't cares have helped me from this cube. This just using the true minterms, I formed this by wrapping around rule. This is again, this is where a don't care helps me to follow this block from this cube. And this is one more. Okay, so can you tell me quickly what are the minterms corresponding to? Let's say what is this blue thing? This blue, yeah, this is the blue 10 and 14. What is the minterm corresponding to that? The reduced minterm corresponding to that? Anybody? Just help me fill up these minterms. Somebody please help me fill up these minterms. They have been color coded for your advantage. Okay, let me write it down.
So A bar, B bar, B
It has
bar.
B.
A bar, B bar. Okay. Now this red thing, very good. Now this red thing, 25, 27, 17, 19, I've included a don't care there. What is that?
A C bar E.
A, C bar E.
A C bar E.
Yes. Now this 1, 3. 1, 3. What is the minterm? 1 and 3.
B bar, C bar
It's
E.
Yeah.
Sir,
B bar,
it is
C bar.
1, 3, 17,
1, 3,
19.
17, 19. 1, 3, 17, 19. You have a wrap around, vertical wrap around. 1,
B
3,
bar,
17.
C bar E.
B bar, C bar E. Very good. And now what about this 8, 12, 24, 28? 8, 12, 24, 28.
B D bar, E bar.
E, D bar, E bar. And what about this 20 and 20?
A
21,
B bar,
20.
C B bar.
A, B bar, C, D bar. And the last one, this 6 and 7.
A bar, B bar, C D.
A bar, B bar, C. Very good. So this is how you should do it. This is another example. This is another example. Can you, okay, now you tell me you just tell the numbers of the cubes that we can form. The goal is, as you remember, we should form as large cubes as possible, consist of adjacent cells and 2, 4, 8 like this. So the cube, although I have don't cares here, don't cares I can conveniently treat as 1. So 1 and 9, 24 and 30. I want to treat them as 1 because they will. No. 1. These are the don't cares. Okay. So now tell me the cubes. You can tell me the numbers that this is a cube. What are the cubes here? You can first try to form 8 sides cubes, then try to form 4 sides cubes, then try to form 2 sides cubes. What is a 8 sides cube that I can form here? In fact, there are 2 8 sides cubes that I can form here. You can tell me the number of the minterms corresponding to these cubes.
Top row.
Yeah. Repeat.
The first row.
Top row is 0, 1, 3, 2, 6, 7, 5, 4. This is one.
And
Fine.
the third
There is
column,
another 8.
its reflection.
Yes. So 3, 7, 11, 15, 27, 31, 19, 23. Okay, so these are the two 8-sided cubes. What are the 4-sided cubes here? Note that I want the minimum number of cubes. So if a 4-sided, of course, a 8-sided cube will consist of two 4-sided cubes, but I'm not interested in smaller cubes. I am interested in larger cubes. If something is not covered by a larger cube, then I'll try to form a smaller sized cubes. Okay, so what are the 4-sided cubes that I can form?
Sir,
0
0
to
to
16,
16, 18.
0 to, very good. 0 to 16 and 18 is a 4-sided cube. Any other 4-sided cube? Any other? There is one more 4-sided cube. There is one more 4-sided cube. Look at the mirror reflection around the middle of the two vertical line, as well as the wrapping.
19,
Excellent.
0, 3.
Excellent, excellent. So let me write. So this is the first row. This is the first row. This is the another 8-sided thing. This is 0 to 16, 18. 0 to 16, 18. Oh, but this was already in. Okay, this is all 0. All right. So let's write down. So first row is A bar, B bar. You can check. This 3, 7, 11, 15, 27, 31, 19, 23. This is CD. The bar is there. No, the bar is not there. CD. Okay. Now 0 to 16, 14. It will be a 3-sided thing. So B bar, C bar. You can easily verify actually. There are no more. There are no more. Okay. So
Excuse me,
this.
sir.
Yeah.
Sir, the red one will it not be DE?
Red one will not be. It will be D. Wait, let me see. The red one is, what is the constant? What is the constant? The constant is D is constant. Yeah, it should be D. It should be D. Sorry, this is a mistake. I'll note it down. This is a mistake. This should be D. Good. All right. So now, so this is fine. I think so. It's a little bit difficult to visualize. You are doing it afresh fine, but sometimes people tend to follow. But you should remember this reflection rule as well as the wraparound rule and the usual adjacency rule. Okay. Now let us go to 6 variables. So 5 variables. What we did, I took this 4x4 block. I reflected along this horizontal axis. So now what we do, now let's say I have this 5 variable, the top half of this table. I have the top half of this table. I reflect the entire top half vertically. I reflect the entire top half vertically along this line. I reflect it. Okay, along this line I reflect it and I get this. You look at the values 0, 0, 0, 0, 0, 1. You see again that thing follows. That means two adjacent cells differ by just one variable, and also they are in gray code order. They are in, of course, naturally they will be in gray code order. Okay, so you just because of this, you remember the reflection property of the gray code. Because of this, you can create this just by reflecting. First, you take a 4x4. First, reflect along the horizontal axis, reflect along the vertical axis, then take the entire thing and reflect along the horizontal axis. So you get this six variable map. And what are the rules of adjacency here? See, algebraically, the rule of adjacency is very clear. It should differ by just one variable. The geometric visualization is involving all this reflection and wraparound and such things. Okay, so these blue ones, let's say, are the true minterms. So you have the usual rule. That means you can wrap around horizontal axis, you can wrap around vertical axis, because now there are 6 variables. Earlier, the largest cube that you can form consisted of 8 cells, but now you can have 16 cells cubes also. You can have 16 cell cubes also. Right. So let's see. So so just like before, two columns which are mirror image along the vertical axis are adjacent. Similarly, here two rows which are mirror image along this middle horizontal line, they are also adjacent. So 19 and 51 are adjacent. 27 and 59 are adjacent. Okay, 1951, 2759 are adjacent. Right. So the same thing that we talked about vertical reflection holds for horizontal reflection also. So can you tell me what are the cubes here? What is the largest cube here? 16 sized. And the usual wraparound, vertical wraparound, horizontal wraparound of individual 4x4, wraparound of individual 4x8, they also hold. So you can, so 0 and 2, 8 and 10, 24, 26, these are also adjacent. These are also adjacent. Okay, so you have the wraparound, you have the reflection, and you have the usual geometric adjacency. And you have because of the wraparound, the corners also you can consider adjacent. Okay, so now what is the largest cube that I can form here? Largest cube that I can form. Tell me which columns will give me.
So the cube of 16 elements containing the first and the last column.
Very good, very good. So that's the 16 element. So let me see. So 16 element means there are 4 variables that I can eliminate. The reduced min term will consist only of 2 terms. So this is E bar F bar. Sorry, E bar F bar. Okay. So what is the? Are there any 8-sided min terms? 8-sided cubes? Are there any 8-sided cubes here? Can you tell of any 8-sided cube? Are there any 8-sided cubes here?
So 48, 49, 51, 55, 53, 52.
No. For 49, 48, 50, 48, 49, 51, but that is not 8.
And 55, 53, 52.
55, 53, 52. But that, okay, what else? So you have 6. 2 more we need.
Oh, sorry.
It has to be 2 to the power k form, 2 to the power k cells. Okay, so it can be 16 or 8 or 4 or 2. Anything else that we have? Anything, any 8-sided thing that we have? Well, I mean, okay, we don't have actually. So 4 sides, this is there. So what you said that 48, 49, 51, they actually are a 49, 51, 55, 53. This is there. Corresponding min term is A, B, C bar F. This is another. This is the wraparound as well as the reflection. 0, 2, 6, 4. A bar, B bar, C bar F. And now we have this individual term. So now 27, 20, 19 you can combine. Okay, so this 15 is a single uncovered min term. 15 is a single uncovered min term, so that cannot be reduced actually. So you have all the 6 variables here: A bar, B bar, C, D, E, F. All the 6 variables are there. Next, this is a 4 variable. Okay, this is a 4 variable. This is 54, 55, 53, 52. So A, B, C bar, D. We still have uncovered, so I have to write some more. So naturally 27, 19, 51, 59. 27, 19, 51, 59, which is B, D bar, E, F. Okay, so these are the rules that you can. So you can find larger patterns, of course, in this 6 variable map. And this is the end of Carnot map. You cannot go beyond 6 variables. Naturally, you can see I have reflected along the horizontal direction, I have reflected along the vertical direction. Now, if you want to expand it further, you cannot form a 2-dimensional map. You have to go to 3-dimension. Okay, you have to go to 3-dimension. And for all practical purposes, visualizing these cubes in 3-dimension is useless actually. It's not very useful anymore. Basically, we are relying on the human capability to discover patterns for the minimization purpose. That's the whole part. That's why we did it. Okay, and beyond this, humans don't have the capability to visualize in higher dimensions. So we are not going beyond this. So 6 is the end up to which you can use. For simple tasks where you have only up to 6 variables, you can still use the Carnot map. But beyond this, you need algorithmic procedures. You need algorithmic procedures to do the minimization. You cannot rely on visual pattern finding. So that is of course very popular, and you know what happens beyond 6 variable is you really don't manually minimize. You actually have tools. What they do, they would use algorithms to do this minimization, and we'll in the next class we'll study the starting of those algorithms. That's the simplest algorithm, the Quinn-McCluskey algorithm. But you can have more complex algorithms. So now things are algorithmic, and people really use a CAD tool, a computer-aided design tool, to do the minimize. Right? We'll go to that. But this is the end of the Carnot map. Okay. So now, so far, what we have done using the Carnot map is that after the reduction, we have expressed the function as a sum of product form. So basically, I have written it as a sigma of m's, small m's. Small meaning the min terms. Min terms means the product terms. So it's a sum of product form. So in order to find the sum of product term, what I did is that from the truth table, I picked up the true min terms and plotted them here. Right. So, but suppose instead of sum of product, you want the product of sum forms. Okay, so you want something like ABC plus D, no, not ABC, sorry, A plus B plus C times D plus E plus product of sum form. So again, this is a two-stage expression. You first apply the OR, then you apply the AND. Whereas in sum of product, you first apply the AND, then you apply the OR. So this is as you can see, this is a product of sum form. And as you know, each term inside this bracket, that is, for example, say A plus B plus C bar plus D bar, each of these terms are called max terms. They are called max terms. Okay. There is an easy way to remember why it's called a min term and why it's called a max term. Because if you assign values to each of these literals, A, B, C, or D, max term would evaluate to the largest value among, whereas the which is 1. If all are 0, it is 0, otherwise it is 1. Whereas in the min term, if you take A, B, C bar, D bar, for example, it will evaluate to the smallest value of these literals. That's why it's called a min term. Okay. Suppose I want to express a function as this product of sum form in terms of the max term. So actually this is represented by the pi. Just as I had sigma over small m, this should be pi over large M. This should be pi over large M. Product over large M. Okay. So what do you do to do this? Note that there is a complementarity or duality among this min term and max term. Okay. So if a particular input combination, if you write it as a min term, the min term will accept it only if the max term rejects it. Only in the max term there. So they are complemented. So what it means, if you try to, when you form a Carnot map, in the min term form, in the sigma form, you picked up the two min terms and marked them. You picked up the true min terms and marked them from the truth table. Here you do the reverse. You pick up the false. You pick up the false rows from the truth table. You pick up the false rows because min term accepts if max term rejects. You pick up the false terms, right? And then we will tell you about the rule of the minimization rule. But let's see. So the cover is obtained in all the places. So instead of marking the true min terms, you mark the you mark all the rows where corresponding to where f is false. But I have to open again. Yes. All right. So let me summarize. So I want to, my goal is to form an expression of this form. I want to minimize an expression of this form. But I want to express it as a product of sum. Right. So my final output will be, so this is a product of sum. My final output will be a reduced expression, but still of this form, because my realization will be of this form. Okay. So the first step is you pick up the rows of the truth table of the function, which corresponds to zero output. It corresponds to zero output, and you mark them. And this numbering are in the same form, 0, 0, 0, 1, 1, 1, 1, 0. But instead of highlighting the true min terms, you highlight the false min terms. So in this diagram, true min terms are blue, false min terms are gray. Now, I don't worry about the blue terms here. I am worried about the, I'll be working with the gray terms here. Right. So now we'll use the same thing. We'll try to form cubes covering as many false min terms as possible. And then we'll reduce it in the exactly identically the same way as follows. Only one difference. Say for example, in the final expression, because my final expression will also be in the product of sum form. Say for example here, can you tell me, anyone tell me this orange thing? What is the minimization of this? What are the binary values which it will minimize to? Anybody? So 3, 7, 15, 11. What does it minimize to? What are the variables?
CD.
CD, right? CD. So if we did a sum of product form as in earlier, we would write it as CD. But here we will not write it as CD. We will write it as C bar D bar. We'll take the complement. So if it is 1, 1, we'll write it as C bar D bar. If it is 0, 0, we'll write it as CD. So this will actually minimize to C bar plus D bar. The corresponding max term will be C bar plus D bar. Okay. Now let us see why this will also give you a valid max term representation. So in other words, is it equivalent to the corresponding min term thing? Okay, so why? But again, why I can do this minimization? In earlier min term case, you can do this because Sx plus Sx bar is S. Similarly here, S plus X into S plus X bar is S again. You can verify this is S again. So that's why I can eliminate X. And again, you have the adjacency rule and all these rules similarly as before we have. Okay. Mm. So let's see. So what I have done here is that let me express f. So let me hypothetically form a f which is a product of all the max terms, which is a product of the max terms. So M3 means a plus b plus c bar plus d bar. This is M3. M4 means a plus b bar plus c plus d. So note here in the top I have written the values of the min term, the decimal values of the min term. Okay, and you know it is a product of some form. So M3 will correspond to a plus b plus c bar plus d bar, a plus b plus c bar times a plus b bar plus c plus d, a plus b bar. So this way product I have written. So this is actually the pi notation. This is pi over capital M 3, 4, 6, 7, 11, 12, 13, 14, 15, which basically means this expression. Right. So this is the f that I want to minimize. Now let me do some simple transformations. By De-Morgan's law, f bar is, if this is f bar is this by De-Morgan's law. Okay, just I have put a bar over the max terms, replace the dot by the plus, and I have the bar over f because of De-Morgan's law. Okay, so what is M3 bar? M3 bar, let's say, because I said that, you know, M3 I'll take complement. So if it is 1, 1, I will take it as C bar D bar. So if M3 is C bar D bar, M3 bar is CD, the corresponding min term. That is M3, small m3. I'm writing it like that. Similarly, M4 bar is small m4. So if I complement the max terms as I have defined, how I have defined the max terms? If it is 1, 1, I have taken it as C bar D bar. 1 is bar, 0 is unbar. Okay, so naturally, if I complement till, I'll get back the corresponding uncomplemented min, but this is still f bar. So if f bar is this min term or this min term or this min term or this min term, if we complement the entire, you will get the reverse, the remaining of the min terms which are not there in this. You will get the remaining of the min terms which are not there in this. Right, remaining of the min terms. And since these are the false min terms, remember these are 3, 7, 15, 11, these are the false min terms. And the remaining of them will be the true min terms. For example, here the remaining of them are 0, 1, 2, 5, 8, 9, 10. These are the remaining, right? These are the remaining. And precisely because everything is either true or false, so the remaining of them will be the true min terms. So, and I put a complement. So f will just be the true min term because I am taking the remaining. This will be just the complement of that. So f is this. So what I have basically proved is that if f is a sum of product form of the true min terms, I can also express f as the product of term of the false min terms. Sorry, product of sum of the false min terms. That's what I proved. Okay, and the remaining rules are as before. Remaining rules are as before in the same. So just as if you have a Carnot map where instead of covering the true min terms, you want to cover the false min terms. Okay, you want to cover the false min terms instead of the true min terms. And this is first variation. Second variation is if a cube reduces to, let's say, CD equal to 1, 1, the corresponding max term will be C bar plus D bar, not C plus D. It will be C bar plus D bar. And finally, as in sum of product, you all take all the reduced term, you add them. Here you take all the reduced term, you multiply them. So it will be B plus C. So can you tell me what is the final expression in this Carnot map? What is the final product of sum for this Carnot map? Anybody? Anybody quickly tell me the product of sum for this Karnaugh map? Just work it out. What is the max term corresponding to 3, 7, 15, and 11? It is C bar plus D bar. What is the max term corresponding to? So it is C bar plus D bar times 12, 13, 15, 14. What is the max term? It is A bar plus B bar. So it will be C bar plus D bar plus A bar plus B bar. What is the max term corresponding to 4, 6, 12, and 14?
Sir, B bar plus D.
B bar plus D. Very good. So it will be A bar plus B bar, A bar plus B bar into C bar plus D bar times B bar plus D. That will be the reduced product of sum form. Okay. So this is how you. So it's just the dual procedure of the sum of product. Everything else is same. So this is the final expression. This is the final expression. Okay, here is another example. This is the pi notation. So this is 1, this is 1, this is 1, this is 1. And so I'm writing down the corresponding values. This is 1, this is 1. All right. Note that I'm looking at the false min terms. I'm not looking at the true min terms. I'm looking at the false min terms. Okay, I think I'm done with this. Let me come back to one more expression. All right. So what we'll do is that, see, I have explained how diagrammatically you can do all this. But as I have said, you have to now algorithmically do all this. For that, I need some definitions. I need some definitions. Let me try to. Okay, this will do, I think. No. So you can actually also, I'd suggest you that you can, sometimes these don't cares are represented by this phi symbol. Phi denotes a don't care in the Karnaugh map. So you can take some examples and do this Karnaugh map minimization for maybe 3 inputs or 4 inputs. Okay, you can or 5 inputs. You can do that. Okay, now let us go to another discussion which will require for our next algorithm. Let me try to write down. All right. Try to. I just want something to write on. Yeah, this will do. Okay, so let's take a truth table. Let's say I have just two variables. In general, I can have more variables. So let's say x and y as the variables, and I have two functions. Pardon my bad drawing. Let me see if I can draw better. Okay, so let's see. And let's write some values here. Let's say 0 and 1 and 1 and 1. And let's say this is 0 and 0 and CRM. Okay, let us start. Yeah, so just pay attention. Yes. Yeah, please, all of you, please pay attention. Let us start. Can I start? Just anybody confirm, am I audible?
Yes, sir, you are.
Yeah, thank you.
Yes,
Thank you.
sir.
Okay, all right. So this is a truth table. Let me quickly, yeah, I'll draw a better diagram. Just I'm taking two variables, let's say, or maybe three variables. A, B, C. Let me quickly write down their values. And so on. Okay, and let's say I have two functions, f and g. Let's say their values are like this. Okay, so let me write some definition. G covers F if all in which F is true, G is also true. Okay, so basically, if you pick up the rows, one rows for F, there will be a subset of the one rows of G. For example, OR covers AND. The OR operator covers the AND operator. So we say G covers F. Right. So in fact, you can easily see that if G covers F and F covers G, then F is equal to G. All right. So what we do is that if this is if G covers F, we say that F implies G. F implies G, or other words, F is an implicant of G. F is an implicant of G. All right. So one thing you can always say that see, if you take a G to if you take a G, for example, say A B C plus, let's say, A bar B C plus, let's say, A bar B bar C, you see each of the implicants, each of the main terms are an implicant of the function. Each of the main terms are an implicant of the function, because naturally, because each of the main terms are corresponding to one row, of the truth table, and since naturally that is covered by the whole function, so each of the main terms will be an implicant. So each main term, rather each true main term is an implicant. So it's easy way to find the implicant. You write down the truth table of the function, take any subset of the true rows, the corresponding expression that you get is an implicant. So naturally, one single row will also be an implicant. Now you see there are larger side row. For example, you see here BC is also an implicant. BC is an implicant. You get, because see, for example, BC will be how many rows? BC will be 2 rows, maybe two true rows. Naturally, that is also a subset of the function, so BC is also implicant. Okay, so there are number of, so can you define the set of implement for this implicants for this ABC plus A bar BC plus A bar B bar C? So ABC is an implicant, A bar BC is an implicant, A bar B bar C bar is also an implicant. Similarly, BC is also an implicant. Anything else? Anything else is an implicant? Can you tell me? In this
A bar
expression,
C.
A bar C is also an implicant. So if you look at the truth table, and if you list out all the, okay, I should have drawn a 3 variable truth table, but anyway, let me draw a 4 variable itself. To pick up all the true midterms, all of them are individually implicant. Any 2 to the power k-sized cubes that we talked about in the Carnot map, they are also implicants. All right. So, so all these boxes or all these cubes that we drew in the Carnot map, each of them are implicants. Each of them are implicant. Any box that you can draw are implicant of the entire function, considering, of course, the sum of product, the true minterms only. Okay. So now, note one thing that we have so now if I look at this implicant, for example, if I look at A, B, C, this is one implicant, let's call it I1, and BC, this is one implicant, let's call it I2. There is an ordering among these. What is the ordering? That we say that BC is an expansion of ABC. Can anybody tell me why I've reduced? I've eliminated a variable, but still I'm calling it an expansion. Can anybody tell why I'm calling it an expansion? Any idea? Any guess why I'm calling it an expansion, not an elimination? Of course, it is an elimination of a literal, but I am calling it as an expansion. Can you tell me why? Because you see, the number of entries in the truth table for which BC is true is more than the number of entries in the truth table in which ABC is true. Okay, so if you draw in Carnot map, the BC minterm, the cube corresponding to the BC minterm, is an superset of the cube corresponding to the ABC minterm. Okay, so the process that you are combining a set of minterms, you are combining a set of implicants in the truth table, in the Carnot map, and forming larger cubes. This is an expansion process. Okay, this is basically an expansion process. That is clear. So I can, for example, I can create an 8-sided. So this 8-sided cube is an expansion of this 4-sided cube that I get by dropping one of the variables, maybe stable, maybe so A, B, and C, D. Maybe I dropped the AB variable, or rather, if you look, if this 4 was, let's say, ABC, not ABC, this will be A bar BC. Then I have dropped the B variable to get this 8-sided expansion. Okay, so there can be a relation among the implicants. There can be a relation among the implicants. In fact, what you can do is that you can nicely represent them as an Hasse diagram. Now forget about this 1011 that I've written, but you can, in fact, I'll explain them also what they mean. I can write them as a partial ordering in the form of a Hasse diagram. Okay, so let us define what are these join. So you know, in any Hasse diagram, there will be you can define a join and a meet. Okay, so let us look at this implicant. Suppose if I consider three variable functions. So these are all implicants that I can have. There are, I mean, not the implicant. These are all the min terms that I can have. A, B, C bar. These are. If I write in binary terms, I can write it as 1, 1, and 0. So these are. Now let's see what is the join operation. Can one? So what is the join between ABC and ABC bar? ABC and ABC bar. What if we apply
AB.
the rule that AB?
AB.
So AB. So what I have written here is that, see, I have eliminated the C variable. That's why in the as a placeholder for the C variable, I have written this dash, or a don't care, you can call it. I have written this dash. So you see, but see, AB is an expansion of ABC. AB is an expansion of ABC bar. So if two implicants which differ by just one literal in complemented and uncomplemented form, they can be joined to their expansions because both have the same expansion. This is the same expansion that I'm doing on both. I'm removing the C. They can have this expansion. So this is the join operation. Now note that what this basically means in the Carnot map. Carnot map means if I have two cells ABC and ABC, I have merged them to form this larger cell AB. This is a two-sided cell AB. Okay. So the join operation in this partial ordering in this Hasse diagram is basically this cube forming operation in the Carnot map. If we write down all the possible, so this is the Hasse diagram of all possible implicants. This is the Hasse diagram of all possible implicants that you can have involving three variables. Note that what will actually happen is that see, this blue thing is the entire space. But let's say this green one. You look at the base of the list elements of this Hasse diagram. You see these green ones. These are the true min terms. Let's say these are the true min terms. This green one are the true min terms, right? So this sub lattice, this sub Hasse diagram, which is obtained by joining only these green min terms, by merging only by expanding only these green min terms. That sub lattice form all the implicants of the function whose true min terms consist of ABC, A bar BC, A bar A B bar C, A bar BC, A bar B C bar, and so on. So this green part are only the lattice formed with by joining the true min terms only. So if we look at each of these green terms, each of these green nodes, let's say in this entire Hasse diagram, they will correspond to all different size cubes that you can form in your Carnot map. So if your Carnot map is like this, this is A, 0 and 1. This is, let's say, BC 0, 0, 0, 1, 1, 1, 1, 0. So what are the true min terms? ABC. ABC is this. A B bar C. A B bar C. A B bar C is this. A bar BC. A bar BC is this. And A bar BC bar. A bar BC bar is this. And A bar B bar C is this. This is my Carnot map. corresponding to this. And you see, so what are my implicants? This is an implicant. This is the base thing, base of this acid diagram. These all implicants. Let us look at this. AC is an implicant. AC, can you tell me what is AC? So AC is an implicant. A bar B is an implicant. A bar C is an implicant. BC is an implicant. B bar C is an implicant. Can you tell me what is AC? What is AC? What I get by expanding ABC bar and A bar BC? So what is AC? Can you mark what cube is AC in this Carnot map? So this is my AC. So this corresponds to this. Similarly, what is A bar B? A bar B. A bar B is this. So this corresponds to this thing in my Carnot map. This thing in my Hasse diagram. Okay. So similarly, what is this? This corresponds to this in my Carnot map, in my Hasse diagram. Right. So all these cubes that you are forming in your Carnot map, you can map them to this Hasse diagram of this primary implicant, where in the Hasse diagram, the partial order relation is an expansion relation. If you get one implicant by expanding another implicant, you can also define a join and meet also here. So in the Carnot map, this is equivalent to merging them to form, this join is equivalent to merging them to form larger cubes, right? So the moment this is there is a notion of something known as prime implicant. Okay. So what is a prime implicant? Prime implicant is if you drop one or more literals from an implicant, it no longer remains an implicant. No longer remains an implicant. Okay. So for example, ABC is an implicant, but it is not a prime implicant, because if you drop C, you get AB. AB is still an implicant. Or okay, let us look at these green things only. So if you drop B, so you have, this is ABC. I have dropped B. I have got AC. That is still an implicant. So ABC is not a prime implicant. Similarly, from AC, I can still drop A and get this, which is also an implicant. So AC is also not a prime implicant. Okay. Okay, so this is, so prime implicant is kind of a minimal implicant, in the sense that if you drop something from that implicant, if you drop a literal from that implicant, it no longer remains an implicant. You cannot drop, you cannot expand it further, you cannot do an expansion on it, and it still remains an implicant. It cannot be that, right? So for example, if you drop B, you get A bar. That is it does an expansion, but that doesn't produce an implicant. Only these green things are the implicants. Okay, so this is the definition of prime implicant. So in the Carnot map, if what it means is that if an implicant is a subset of another implicant, it is not a prime implicant. So prime implicant is one such box, which is not a proper subset of another box, another valid box. It should not lie completely inside. So, so if I take a Carnot map like this, if we take a Carnot map like this, and let's say these are the, okay, so this is one implicate, this is one implicate, this is part of this, so this is not a prime implicate, whereas this is a prime implicate. Similarly, this one is a prime implicate because this is not entirely lying inside this, so this is a prime implicate. All right, so you cannot drop something, it's called a prime implicate. And so you see the final expression that we have, if you remember the process of the Carnot mapping, is nothing but the final reduced expression is an union, is an summation of all the prime implicates which cover all the true, the prime implicates which cover all the true min terms. If you take their union, if you take their summation, you get the final expression. So as a theorem, you can say that the minimal sum of product expression of a function should contain all the prime increments that cover all the true min terms, all the prime implicates covering all the true. It's a union of them, right? But how do you find prime implicates? You actually need a search algorithm. You actually need a search algorithm over the truth table to do that. That we'll talk later. Okay, so there is another notion of that often. Note one thing, that there may be multiple prime implicates. There may be multiple prime implicates. And it is also possible that one prime implicate can be thought of as a linear combination, as a sort of combination of other prime. For example, let me take this. Okay, so here, see, this is a prime implicant, this is a prime implicant, this is a prime implicant, this is a prime implicant. So all these are prime implicants. You cannot drop anything from there, in the sense that none of them are completely contained inside another prime implicant. So all these are prime implicants. This is sometimes called a circular Carnot map, circular prime implicant chart. But you see that this prime implicant, let me see if I can change the color. You see that this prime implicant is covered by this prime implicant and this prime implicant. So if you have this and this, you no longer need this. You no longer this. This is covered by these two. Right. But whereas this prime implicant is not completely covered by other prime implicants. Is not covered. So the definition is that an essential prime implicant is a prime implicant all the elements of which cannot be covered by combination of other prime implicates. Okay, so you cannot cover it. So because why you are looking for essential prime implicants? Because if it is not essential, if we have the other ones which cover this, then I might as well see, my final goal is to cover all possible input cases, is to cover all the rows of the truth table. I want to cover all the rows of the truth table by my function, by my expression. So basically in the Carnot map, I want to cover all the two minterms. So if it is, so naturally first thing I look for is prime implicant, because that will give me the minimal expressions, the smallest expressions. I'll also look for essential prime implicants, because I have to have the essential prime implicants, because it definitely has at least one element which cannot be covered by the other prime implicants. So in summary, the final reduced expression that we want to have has to satisfy two conditions. First thing is that it has to be an combination, it has to be an union of prime implicants only, otherwise it's not minimal. It has to be an union of only, so if we look at the final expression, if I look at individual terms, each of them will be prime implicants, each of them has to be prime implicants, right? Prime implicants in the sense they are minimal implicants. First condition. Second condition is that, that leaves options. That leaves options in the sense that since there are multiple, you can cover the same set of true minterms by multiple set of prime implicants. By multiple set of prime implicants, you can one combination will cover, another combination will also cover. So it has to. So this leaves some options. There can be multiple minimal expressions. So the first rule is that if you look at the final expression, it should contain only prime implicants if it is minimal. Second rule is that it has to include all the essential prime implicants. It cannot leave out any essential prime implicant. It can leave out a non-essential prime implicant, but if you have found out an essential prime implicant, you can almost be sure, not almost, you can always be sure that they will always be present in the minimal expression. They will always be present in the minimal expression. So the first job you do in order to find a minimal expression is identify your essential prime implicants and include all of them. They will be there. Without doubt, they will always be present in the final expression. Now, the remaining ones, remaining true minterms, you can cover, and you have to cover them only using minimal prime implicants. If you want to have a minimal expression, you can cover them only using prime implicants. You cannot cover them using just implicants. Then you have not done a reduction. You have not done an elimination. Right. So this is the rule. So with this, I end. In the next class, Professor CRM will tell you about an algorithmic method of finding out the minimal expression. Because so far I have talked about only diagrammatic methods. As you have seen, they do not work beyond 6 variables. Okay. So thank you. Thank you. I think if you have any question, you can ask.